I am Steve Ferguson. Join me as I guide you through the test methods of MIL Standard 461F. Welcome to the lab. As we discussed back in the cafe, we want to do CE101 calibration verification. This involves a process of a signal generator. Our particular one happens to have an amplifier built in. This is connected to this resistor that we discussed in our drawing. The resistor we've selected as 30 ohms, and we verified this thing to be 30 ohms. So with that, we can now calculate what our applied current should be and the voltage that we should measure. We take the 30 ohms, bring it into our measurement system, and our limit has been determined to be 110 dB microamps. So minus 6 dB would be 104. These happens to be the same numbers we discussed in the cafe. And with the 30 ohm resistor, our current probe factor gets into the equation because we have to consider it. So our current is 158.5 milliamps. And that means that in order to produce 158.5, the oscilloscope, or the measurement device, the AC voltmeter, should see 4.8 volts RMS. Let me go over and connect these items. The oscilloscope gets connected across the resistor so we can measure what's being applied. And the current probe gets placed onto the loop so we can measure the current flowing in the system. With these all connected, we're now ready to take some measurements. Our first step is to adjust the signal generator to produce the 4 volts RMS at 1 kilohertz. We produce this item. We're measuring with the oscilloscope because we don't calibrate this signal generator. So I'm observing the level on the oscilloscope and adjusting the amplitude until I get to 4 volts RMS. And I have 4 volts RMS as displayed on our measurement system right here. So we should be able to now take a measurement of the current flowing through the system and verify that our system is working correctly. With that, I'm going to use our measurement software and select a value of 900 hertz to 1.3 kilohertz as our measurement point. Because we're centered around 1 kilohertz, so we span that area. We start the software and tell it to run. We select our current probe that we're using, and the current probe we chose was number 615. We use this filing naming convention so we can call up files from our calibration system till we know the correction factors. This list selects our equipment in use. For instance, cable number 485 is the one that comes from the current probe to our analyzer. So now the system knows to look up those correction and conversion factors when we start running the software. We select a file name. We're going to call it Cal101 for simplicity, and execute the software to run. And when we start this system, the measurement system drives the analyzer using the right bandwidth for the MIL standard and collects the data. We notice that we have a measurement here showing up on the chart that's produced, and our goal was to be 6 dB below the limit. And I have approximately slightly over 5 dB of difference between the limit line at 1 kilohertz and the actual measurement. We're allowed plus or minus 3 as we discussed earlier, so this system says I am working properly at 1 kilohertz. Our next step would be to go after the next frequency. We adjust our signal generator to a new frequency of, not the amplitude, the frequency, to go to 3 kilohertz. 3 kilohertz. And these frequencies that we're adjusting to are defined in the MIL standard to be used for our calibration verification. Our mathematics, our spreadsheet that we use to simplify our numbers, says we want 1.5 volts RMS at 3 kilohertz. We're slightly above that. I'm going to adjust where the oscilloscope reads 1.5 volts RMS. And we are there. All I do at this point is I go back to our data collection software, select this frequency range of 2.5 kilohertz to 3.5 kilohertz so we can measure the next sequence. Go, same equipment, the same sensors, etc. in use, so I continue. And we overwrite the file. In fact, when we select overwrite, that means we're appending data. So I have to replace it to append the data. And we execute this frequency and collect the data. And we plot that this measurement is now, in fact, 6 dB below the limit. It's measuring more close to 7, but it's well within our tolerance of plus or minus 3. So we're saying that this system is working very well. Our next frequency point would be to go ahead and collect the data for 10 kilohertz. So let us do that. And quite frankly, I don't like to do 10 kilohertz because it's at the edge of our chart. So I go about 9.8 to 9.9 kilohertz, just to be not on that upper line. So we got 9.9 kilohertz, and we go back to our spreadsheet to determine the value. I should see 475.5 millivolts with this same set of hardware. We adjust our oscilloscope to measure 475.5 millivolts. It's very sensitive to get to that number. We adjust this. So there's about 475, and we should only need to execute our software to go 9 kilohertz to 10 kilohertz for our frequency span. Run the software, the same hardware is in play. We overwrite the file one more time. Yep. And we should collect a piece of data that shows that this measurement should be approximately 6 dB below the limit, and it's in fact about 4.5. Again, we're within our 6 dB plus or minus tolerance. So we're very good with our limits. This is in fact a calibration verification. We've seen our system is working correctly, and we have data collected to demonstrate this. This chart would be used in the report to demonstrate compliance prior to doing the test. At this point, we're ready to proceed to doing the testing for CE101. Now that we've completed the verification of our calibration for CE101, we're ready to do the testing. Observe that the test article is now configured, and I'm going to attach the current probe at the right point on the cable and start this testing. As I go over there, I'm going to point out our test article is sitting kind of behind our test equipment here, with the cables arranged as specified in the standard. And we come over to the network. And remember that now we're exposed live terminals, so we kind of stay away from them and use caution. I've selected the phase lead for testing. I place that in the current probe, observing some basic safety. I stay away from those terminals. And I verify my position is 5 centimeters from the terminal. We know this by eyeball, virtually. And so now we are connected with the cable and probe that we calibrated. And all we have to do is run the software to collect the data at this point. So let's go back over and execute the software. I've selected the start frequency to be 120 hertz because the software, the standard says we start the test at twice the power line frequency. Since this is a 60 hertz system, we start at 120 hertz and go to 10 kilohertz. Our software checks everything for the mil standard. We selected mil standard 461F. Well, actually our system says E, but this test is identical. So we basically just run the software. We select the probe that we calibrated. And it's probe number 615 from our calibration, you'd remember. And the cable is 485, and that's the same as we checked our calibration. And we have nothing else in the list. We continue this and we select a file name. We're going to call it CE101 101 phase lead, PHASE, phase lead. So file name is set up, and then we want to do the execution of the software. The software should execute throughout the system and measure the emissions and compare them to the limit. Now, our software settings need to provide for the cycle time of the test article, and now we can see that our test article is in fact compliant with the requirements. This is set up in the monitoring mode, so there's no real activity processing wise. So our limits are set, the 110, etc., and these are the emissions profile for that particular test. We would do this test again on the neutral lead to be complete, and if we have to do all the phase leads, etc., so each individual lead. If we get into trying to find problems, sometimes we will use various techniques that we discuss in other areas regarding troubleshooting and using the probe for measuring things outside the normal test. However, this is the final test on that item, and we could repeat on the second item, but for this demonstration, we'll just limit it to the one test. Thanks for joining me on this Mill Standard 461F test method review. I hope you find it helpful. I also hope you find the time to join us through the complete journey for Mill Standard 461F via the Espresso Engineering series. Thanks for watching.